In this lesson, we're going to explore how to solve vector questions in terms of diagrams that are given to you, for example, in this format, right? So we're going to explore some ideas before we head into the question, and then we're going to see how to solve them actually. The first part of this syllabus question is from moments, and I will be making a separate video for that. You will find the link in the description as well, right? So this lesson only deals with the fact how to look at vector questions and how to solve them if they're graphical in nature. So first we need to understand what is head-to-tail method and what it looks like and how to visualize it. So in head-to-tail method, what we are supposed to do is we are supposed to join 2, 3, 4, 5, how many vectors are given in the question in such a way that they come back to the original position or that their resultant eventually becomes 0. So for example, in this question, if one vector is given in this way, one vector is given in this way, then it's my choice to connect this one vector with this one by this head-to-tail method. So what is head and what is tail? So this is the head of the vector, and this end is known as the tail of the vector. So I choose to connect the tail of this vector with the head of this vector. So this vector looks like this one. So I can now remove the vector given in the question to simplify my answer, right? So now, since there are only two questions or two vectors, if I want to find the resultant, I will connect the tail of the first vector and join it with the head of the last vector. This is what head-to-tail method looks like. So in most of the questions regarding this topic, they will require you to find a system in which the system is in equilibrium. Now, I will explore more about this equilibrium condition, what it means in physics. But briefly, I will tell you, equilibrium position would mean that the resultant forces, according to F equals to ma on the system, are equal to 0. The object is not accelerating, or the object is eventually not moving in any direction. And the second condition is that the resultant torque on the system is 0, which means basically that the moment of the system is equal to 0. This means that there is no rotation. The system is not rotating or it's not trying to rotate. Similarly, over here, the resultant force would mean that either the object is at rest or is it moving at a constant speed. So this is what we mean by equilibrium, right? I've explored this in the second video, in which we explore how to solve the questions regarding moment, the seesaw example, and how to visualize moment, not momentum, moment, which is the turning effect, F into D, force into distance. So let's explore a more complex example. Let's say that there are more than two vectors given in the question. So let's say that an object is experiencing a force in this direction, a force in this direction, and a force in this direction. If he mentions, or if the examiner mentions that this system is in equilibrium, then let's call this vector A, let's call this B, and let's call this C. If he says specifically that the system is in equilibrium, that means you can choose any vector to start your question from, but combined, they should complete a vector diagram that should look something like this. So let's say I start with B. So let's replace B according to the direction that is given in the question, then replace C. Again, by the head-to-tail method, this idea stays. Then the C looks like this, for example. And then when you replace A into the situation, you realize that this A, when connected, is actually in the same direction as represented in the diagram. If this is the case, then most definitely the system is in equilibrium and the resultant forces or the resultant torque on the system is 0. Now, this is one way of looking at it. Another way of looking at it in which the example may show that this is not in equilibrium, then you have to look at the length of the vector. The length of the vector actually represents how large that vector is. Now, for that example, let's say that if a vector is this much, I say that this is 10 newtons. If I want to represent a vector of 20 newtons, then it should be roughly at least twice its length. So the length of the vector is representative of how large the value of this vector is going to be in comparison to the rest of the vectors in the question. So let's say if I had a system like this one, in which this vector is very large and this vector is very small, and I have a third vector given in the question like this. So let's say this is A, this is B, and this is C. And if I were to apply the head-to-tail method to figure out whether this is in equilibrium or not, then it will be my choice. Let's say I replace C at position A. So it will be exactly in the same direction as C. It will be at exactly the same angle as C. It will be exactly the same length as C. That is what we are doing in head to tail. And then I replace this vector B from the last starting position of C. So when I replace B in the situation by copying exactly the same style, I realize that B is going somewhere along this line. So this is where B ends. Now the whole question was actually starting from this point. This was the starting point of vector A, or you can say the tail of vector A, and this is the head of B, the last vector. So if I want to find the resultant, this will be the resultant, or this is the resultant that is going to look like. So this system is not in equilibrium because the resultant is not equal to zero. There is still some resultant, whatever that value may be, right? So I've explained roughly how to check a system in terms of different perspective, at least visually speaking. So let's move on to this loop rule trick for resultant equal to zero or system being equilibrium. What does this loop rule mean? This is not an official word in physics. This is not an official word of the syllabus. This is just something that I've observed while solving questions. And this helps you to quickly figure out whether these options are correct or not. So for a system to be in equilibrium, again, I go back to the system, to this word equilibrium, because it defines two situations. There is no resultant force and there is no resultant moment. The object is not rotating and the object is not accelerating or it is not moving, right? So for example, if we want to talk about this object, let's say that we have an object that is placed on the floor and there is another force acting in this direction, let's say, but the object is not moving from its position. So let's say this might be the weight, right? And this might be the normal reaction coming from the floor. And there might be another force involved here, that is friction, which is eventually causing this object to not move from its place. But we're ignoring that for now because we'll only talk about three forces for this example at least. To understand what is that loop rule. So if I make the head to tail diagram for this scenario or for this situation, right, it should look something like this. If this is the force F, right, and this is the force, let's say W, and let's involve the friction over here because that makes more sense in this situation. So in this case, this will be the friction, right? But if I want to apply this loop rule, how to see this, how to visualize this? Pick any vector. I'm ignoring normal direction for this, right? Because it doesn't fit in this example right now, for three vectors at least. We'll get to that later. Okay, so if I look at this example that is represented, that is just I've drawn with the head to tail method, and I want to apply the loop rule. If I know that specifically that the system is in equilibrium, then this loop rule will apply. Choose any starting point, either choose F, W, or the friction. It does not matter. But follow the arrows. If you follow the arrows, you see that this is pointing thisward, this is pointing towards this side, this is pointing towards this side, and this is pointing back to F. If you notice, there is one complete loop that is being formed if I follow the directions of the arrows, which are joined together by the head to tail method. If I find this example, then most definitely the whole system is in equilibrium. We will apply these tricks and rules, what I've just discussed with you, in the incoming questions, right? So loop rule is a very quick way of dismantling a question whether this is in equilibrium or not. Okay, so one more thing in terms of vector diagrams, or in terms of at least coplanar forces, in terms of visual MCQs and questions. There is another question in terms of forces, right? So if I, let's say, draw another object, and that is actually the common intersection point. Common intersection point idea, right? So in physics, if an object is in equilibrium, then if you extend all the forces acting on the object, they should pass through a common point, common intersection point. What do we mean by that? For example, if you have a ceiling and you have an object hanging in this situation, let's say that there are two threads connected to the ceiling that are connecting the object, that are trying to hold the object back, and this is, let's say, the component of weight, right? Now, according to the common intersection rule, if all the forces are extended, then they should meet at a certain point. They should all meet at a certain location. So if I extend this vector, and if I extend this vector, and if I extend this vector, we realize that the tension components do meet at this point, but the weight component is a bit slightly off. It's a bit away from that common intersection point. So this system is not in equilibrium. Let's explore another example. Let's say that we have an object, a force in this direction, a force in this direction, and a force in this direction. Again, I will extend the forces using a ruler and a pencil. You can do that for MCQs and extend the forces as much as you can. So extend the force, this one as well, and then you extend the third force as well, or as much forces are drawn in the question. If you extend this one, you realize that they are passing through this common point of intersection. This is in equilibrium. So whatever tricks we have learned, whatever thought process we have learned in this question, we are going to use them in the MCQs that I'm just going to solve in this lesson. Okay, let's move to the first question. So the first question suggests you can pause the video and read the question yourself, and you can try to solve the questions on your own before looking at the solution that I'm going to provide. So the first, it says that which forces are in equilibrium, which systems are in equilibrium. So there are two methods I'm going to solve this with, and then it's your choice which one you prefer. So I can use head to tail method, and I can replace this vector. Let me zoom in a bit for this. You can see that large images. So if I move this vector to this position, so it's going to look something like this, right? And then by head to tail method, I have involved this one, so I'm not going to think about this one. I'm going to think about this one now. If I join it downwards, exactly the same way, and you can see that the length of this vector is not as long as this one. So don't try to force this vector to actually be longer than the vector that is in the diagram. Now I can see that this diagram has finished. Okay, so I've included this vector, I've included this one, I've included this one, the diagram has ended. And from the starting point of the first vector, which is the tail, and the head of the last vector, I see that this is my resultant. Is it 0? No, it's not. There is still going to be some resultant. Okay, although this common intersection point test fails in this situation, because if you extend this force, if you extend this force, if you extend this force, they are passing through the common point, but the resultant is not 0, right? For that, we have to visualize it in this way to counter this idea. Consider these two vectors. The average resultant because of them will be approximately in this direction, right? Because if you want to, let's say if you apply head to tail method because of both of them, then this vector will be applied in this direction, right? So the resultant will be in this direction. Is this exactly being balanced by another vector on the other direction? No, it's not. We have another vector that is going somewhere else. So the system is not in equilibrium. You can check this with any method that you like, right? Okay, so I'm going to explore this option C as well. So let's replace this vector over here and then replace this vector over here. I realize that my final resultant looks like this, the start of the first vector to the head of the last vector. This resultant is not equal to 0. It should have come back to the original position. And similarly over here as well, if I replace this vector at this point, it looks like this. And I replace this vector at this point, it looks like this. Again, it has not come back to the starting point. The resultant is not 0. But if you look at option A, what I can do is I can choose this vector and draw it somewhere along this line. And then if I choose the other vector, this one, then I draw it along this line. So it has come back to the starting position. The resultant is going to be 0. Plus, it also you can say accepts, or it also follows the loop rule. You see, it is going towards this direction, then it's going towards this direction. The red arrow and the blue arrow is going towards this direction. The loop is complete. So in this diagram, the resultant is 0. So the system A is in equilibrium. So the tricks I've taught you, you can apply any one of them which you are comfortable with. Now let's move to question number 12. You can find this question, at least this question in mathematics as well in vectors when you have to solve I, J, K questions in three-dimensional vectors. Now, this is just a hint of that topic as well. But anyways, so it tells you what is the displacement of P minus Q. First, you need to identify that vectors are actually represented with their signature, with their sign. So if I say that this vector is P, then this vector will be negative P. So the negative sign, mathematically speaking, represents the direction. So if I have to open this up, then this actually looks like P plus negative Q, which means that this vector Q will actually be drawn in the opposite direction to be represented as negative Q. So the resultant in this situation would be simply in this direction. Or if you want to go a bit deeper, then you'll have to reproduce this vector Q on the head of vector P. This is your vector negative Q. Then the resultant is from starting point to the ending point. This was your starting point, and this is your ending point. So this will be your resultant on average. Now let's see which option actually matches this direction. Option A is wrong, option B is wrong, option C is wrong. It has to go somewhere towards the left side. So the only left direction we are left with is option D. B could have been the answer, but the direction is roughly wrong. This direction is basically if a student has mistaken P and Q to be in the same direction and has ignored the negative sign of Q, then B would have been the answer. But right now it's D. Okay, so in this question, we are going to apply the loop rule, and you will see that how conveniently it solves questions for us without any hassle. So we want to test for all the questions. If you want to try it yourself, you can pause the video and see for the answer later, right? Okay, so let's discuss this. So let's try, he says equilibrium. So I'm just going to try the loop rule on all options. I can see that option A follows this loop and then follows this loop. This is correct. But when I go to the opposite side, I see that this vector is trying to go towards this side, but my direction is towards the left. So the loop rule fails. So this system is not in equilibrium. Okay. Similarly, in option B, I try to go from this side, but this vector is coming from this side. So the loop rule is unable to complete inside this triangle. So this option also fails. Now, when I go to option C, let's start from this point. I follow the direction. Okay, that is fine. I follow the loop direction. That is also fine. But when I encounter this point, I realize that this vector wants to go towards this side, but this vector is trying to go towards this side. So again, the loop rule in this situation also fails. So option C is not the right answer. Now let's see in option D, if you pick any side, right? So if I start from this position, I'm trying to follow this direction according to the arrow. Then I follow this direction according to the given arrow. Then I follow this direction according to the given arrow. And I see then one complete loop can be formed in this example. So option D will be the correct answer. This is how you apply the loop rule. Let's try one more question in this situation. Pause the video, try to apply the loop rule and see if you can find the answer. But I'm going to solve this now for you. You can pause and you can try. So again, it asks me about which system is in equilibrium. I am not going to waste time, just going to quickly apply the loop rule trick and see whether it happens. So F goes to this side, W goes to this side, and then R goes to this side. Luckily, option A is our answer because it is following the loop rule. But let's not dismiss this very quickly because we know that loop rule in some examples may fail. Then we have to overlap and we have to make this diagram again to see whether the length of the vector, by length we have to check the question, right? But it's not the case in this question. So let's take this example. So R wants to go towards this side, F wants to come from this side, loop rule fails. W wants to go from this side, F follows the same direction. It's so far so good. But when I go to this side, no, R is in the opposite direction, loop rule fails. This is not the answer. In option D, R goes to the same direction as W, so far so good, but opposed by F at this point, so loop rule fails. So the answer is going to be option A. This is another common question in terms of forces, coplanar system, shelf with a wire and a hanging sign. So it tells you that the weight of the sign has a weight of 20 newtons and the tension in the wire is 40. So this tension is 40 newtons. So which example actually shows that the system is in equilibrium, right? So again, apply the loop rule. You will see F wants to go towards this side, this does not, loop rule fails. Similarly, if it wants to go towards this side, again the loop rule fails. In option C, we can see that F is in the same direction, 20 is in the same direction, but 40 is not, so loop rule fails. In option D, we can see that it is 40 in the same direction, F in the same direction, but 20 is opposed, loop rule fails according to the arrow. 20 wants to go towards this side, your 40 and F is going towards this side, loop rule fails. So we can go towards this direction, so pick any side and you will see loop rule is completed. So 40 is towards this side, 20 towards this side, F towards this side, loop, there is a complete loop being formed. So this is a system that is in equilibrium. Now let's figure out one interesting thing. Where is this third force F coming from? Where is this force coming from? It says that it is at point X. This is at point X. But where is it being, what is the direction? This is the direction of F. But where is it coming from? Where is that force being originated from? This is basically the normal reaction. If you apply a force on any surface, it will apply a force counter to you at 90 degrees. Similarly, at this point, there is a normal reaction force with the wall where the pole is touching the wall, right? So this is that F that is existing at point X. This is point X, right? So this is the normal reaction from the shelf of the thread that is passing over it. So this thread in contact with this edge is actually experiencing a normal reaction in this direction. That is this force F. Although this is not discussed here, but I've just displayed to you what is normal reaction, where it's coming from, especially in this example. Okay, so this is where vector length is important. This is where you learn that vector length is going to play a role in the questions. So he asks you that this is a system that they have. This is H, a force coming from the hinge or from the wall. How is this force being formed? Be advised, this is actually the resultant of this normal reaction and the force of friction that exists between the hinge and the shelf. So if you see that this is the resultant, this is because of normal reaction and the friction that exists between the hinge and the flange, right? But we're going to ignore the normal reaction for now because that's not a part of this question. That's not required for this understanding. Again, I've just drawn this for you because this will be a part of P2 questions at least. So he's asking me which is the increasing order of magnitude. Out of these three forces, which one is the largest and which one is the smallest? Don't be confused by increasing. Increasing would mean that we have to start from the smallest, go towards the largest of them all. Now, I would advise you to first take out your rulers. And if you can find this question in October, November 2003, it's a very old question. Measure these lengths with your ruler. Now, some teachers may argue, some people may argue that this diagram is not drawn to scale. So what? It doesn't matter. It's quite possible that in real life, this is 2 meters. You can't measure 2 meters with your ruler in real life. It doesn't matter. But if this is 2 meters, then for the sake of diagram, whatever scale he has chosen, that 1 meter represents, let's say, 5 centimeters, the same scale will be applied for H and W as well. If they are shorter, then in real life, they will also be shorter than T. If W is shortest, for example, then it will, in real life, it will be shorter than T and W as well, T and H as well. So whatever scale the examiner has used to make this diagram, that will be accepted throughout the course, throughout this question, because they are vectors. They're talking about vectors, and length in a vector is important. It shows how long or how large this is going to be. So if you take out your ruler, you will realize that these are the lengths that you will find out. It is possible that for you that these lengths come out different. Why? Because during printing process, the size of the page and the setting of the specific key binder can change. So it doesn't matter. What will you find is what's important. You will find that T will be the longest. For my calculation, it's coming out as 1.16 millimeters. H will be in the middle and W will be the smallest. I will advise you to at least print this question and then you can see for yourself that T will be the largest. So then we realize that if we are going to go from increasing order, then I have to write the smallest one first. So W is the smallest, then I find H to be the largest, and then I find T to be the largest. So this is my answer to this question. I've only included this lesson in my class or in this video because I understand you forget about this point, which is as basic as O levels, right? Okay, so now we understand the one of the more perspectives in which the examiner can trick you. Now we find that common intersection trick application. You may be reminded of this as over here when I discussed it, that when you extend all the forces, they should part through a common point. That system will be in equilibrium. If they don't, they will not be. But this question is a bit tricky. This will be a bit tricky. So I'm going to skip this for now. I'll solve this at the end. But this question is a bit easier, right? So I'm going to zoom out a bit. So he asks me which system is in equilibrium, right? So I'm going to extend all the forces by using the same color for all the examples and see where I find the common point of intersection. So this fixed point, I will extend it like this. Again, in this example, I extend it like this. For this fixed point, I extend it like this. Excuse my drawing, right? And for this one, I extend it like this. Now it will be very evident to you in this exercise that option C is the answer because I can find the common point of intersection. But for the sake of understanding, and for those who still don't understand, we're going to complete the question. So I find the increase or the full length of R in this direction, then length of R in this direction, then R in this direction. I would advise you to again print this question, pause the video, take a screenshot, print this question, and use a ruler and a pencil for this question. Okay, then you'll find it to be more easy to be solved. Then for the weight, I use the green color and I draw this as straight as possible that I can. And then now notice that weight is actually drawn from this point downwards. But I'm still extending this as much as possible so that I can find that is there a common point of intersection or not. Now we see that over here, there is this part missing. They could not meet at a single point. Even in this question, they could not meet at a single point. They are unable to pass at a common point of intersection. Even in this question, there is no common point of intersection. But in this question, I can see that there is a common point of intersection. So this question, option C, is in equilibrium. Now we will look at a question in which this trick fails. What would you do then? So this is a question taken from October-November 2013, paper 1.3. 1.3 is usually a bit difficult than 1.2 and 1.1. But let's see. So in this question, I'm going to apply the same idea that I've applied before, right? But I will solve this a bit differently. So just hold on for a moment so that I can draw straight lines for all of them. Okay, just pause for a moment. Okay, so thank you for holding on. So in this example, now you can see that what I've done is extended all the forces given in the question as much as possible, and you're going to do this with a ruler and a pencil on your piece of paper on P1, right? Or during practice as well. So you can go back to the video, take a screenshot, print this, and then try this question on your own, or you can just take a screenshot of this and then compare it with your notes as well. So if we can see very well in option A and option C, we can see that there is a gap in all the forces where they are unable to meet, where they can't meet. There needs to be a common point of intersection, and in C, there is nothing common over here. So option A and option C were not in equilibrium, or you can say they are not in equilibrium. But when we apply the loop trick rule or the extended vector rule in these questions, we see that option B and option D have a common point of intersection. There is a common point of intersection here, and there's a common point of intersection here as well. So now, which one will be the answer? So if you encounter this problem, then you have to go back to the very basics, which is head to tail method. So in this question, you have to apply that, and let's see what happens. So if I apply this green vector and I draw this like this, and then I apply this W vector, which is blue one, and I draw it like this, and then I put in this red vector, which is in the direction of R, we realize that it goes somewhere in this direction, right? So this is, the first one is S, this one is W, and this one is R. And our resultant is supposed to be, in very basic O-levels definition, from the tail of the first vector to the head of the last vector. So it has to go in this direction. This resultant exists. This is not zero. It is not zero, which means that this is not in equilibrium. But if we try this with option B, I see that R is in this direction, right? This is my R, and W is somewhat in this direction. But if I connect S, that goes back to this position as S. Now, if I apply the same head to tail method, and I say the tail of the first vector and head of the last vector, there is no distance between them, which means that there is a complete loop rule being formed in this example. So option B is my correct answer. What you can do is use your ruler, apply these ideas, and draw this on a piece of paper and try this question again. You will see that this is the case for option B. Okay, so let's visualize this from one more example, from one more angle. I'm going to pause at this point. You can take the screenshot because I'm going to erase this solution and make a new one. Okay. All right. So in terms of the new idea or the new solution, right? So if I visualize only two vectors for the sake of example, right? So I'm going to visualize two vectors like this, and I know the resultant is going to be somewhere in between them. But if I involve the third vector, then I have to involve it after I'm done with the first two vectors. Now let's do that in this example. I'm going to erase the solution. Okay. So now we know that the answer is option B. Okay. Let's do that for this example. So if I extend this R, if I look at this R, the red vector and the blue vector only. So the red vector goes somewhere along this line and the blue vector goes along somewhere this line. So the resultant is going to be somewhere in this direction. I can see this very clearly. I can see this very easily that this vector S is roughly in the same direction or in the opposite to the resultant of the red and blue vector. So this is again equal to zero. The resultant is zero. What's actually happening is that if these vectors give me a resultant in this direction and I involve a third force which is exactly opposite to this one, it is as good as zero. The resultant is zero because whatever these two vectors were generating is being balanced by, it is being compensated by a vector that is exactly in the opposite direction. And if this is difficult to visualize, then how about this example? If I apply a force of 100 newtons in the front and apply 100 newtons in the back, the resultant is zero. So something similar is happening in this situation, that these two vectors produced this resultant, And if you involve a third vector that is exactly opposite to this one, the resultant is going to be 0. Similar thing has happened in option B as well. So this is another way to look at this. In option D, if you try to apply this, you will not find a solution like this one. Okay, so if you apply the red vector to be in this direction and blue vector to be in this direction, the resultant will be in this direction because of both of them. So if you involve the third vector, which is the green one, you realize that it is actually in this direction. So the resultant and this vector combined are going to produce a resultant in this direction. So the resultant is not 0. It is not being balanced out. Over here, we can see that the resultant of blue and red produce the green vector, the purple vector, and the green vector, which is this S, is actually opposite to their resultant. So the option that very closely follows the resultant principles of 0 or equilibrium is option B. I solved this question in detail from every angle possible so that you can apply these ideas on other questions of visual representation of vectors. I'm going to erase the solution and then I'm going to move on to the last question. So now we move on to this blank example question. This is another very common question in physics. He tells you that in which situation, what will be the direction of resultant, whether the plank is going to fall, whether the plank is not going to fall. But first, I would like to show you an animation of what this system is actually going to look like. What is he talking about? So there is a wall, there is ground, there is a plank or a ladder. What's happening with this ladder? How is this actually going to move? If we can visualize the movement, then we can visualize where these vectors and where these forces are actually going to come from. So I'm pausing the video at this point. I'm going to show you the animation and then we can move on from that point. Okay, so now we're going to see this animation. This is assume the left side to be the wall and the lower side to be the ground. Okay, so I'm going to play this animation and see what happens. So this is how the ladder or the plank is actually sliding down. I'm going to pause at this point. You can see that this lower point is moving forwards and this upper point is moving downwards. So the slide or the ladder or the plank is actually moving downwards. It's sliding down. So let me complete the animation. So this is how it's going to go. Let's play this once more so that you can visualize this properly. And the ladder or the plank eventually falls. Okay. So now we have seen the visualization, how this ladder or the plank is actually moving about, how it's actually going forward. Now we can understand what might happen with the forces. So first and foremost, let's simply note down and understand what are the forces at play in this question. So this is the wall, this is the ground, and this is our ladder or plank standing at this point. First, let's figure out what are going to be the forces. First, there will be normal reaction from each surface. And we know that normal reaction is supposed to make an angle of 90 degrees from the surface like this. So this is normal reaction, and this is also normal reaction. And now I realize that the plank was actually falling down, as shown in the animation. You can go back and visualize it again. So this point is moving forward. That means the friction will be backwards. And this point is moving downwards. That means the friction will be upwards, because we know that friction is always going to oppose the motion. So that is how we predicted the direction of friction in both situations. Now, if this is the case, then we must also be able to draw the direction of the resultant because of these two forces. So the resultant, because of this friction and this normal reaction, will be somewhere along this line. So this will be the resultant of the wall. And in this case, this will be approximately the direction of the resultant of the floor. Again, normal reaction and friction are involved. If you want to visualize it simply, then it will be something like this. So the resultant is going to be somewhere in the middle, right? So what the examiner does is going to give you the resultants only, okay? Now be advised that if he says in the question that the floor or the ground is smooth, that means that the friction does not exist. If he says that the ground and the wall are rough, then the friction exists. So if the friction ceases to exist, then only normal reaction will be the resultant of that situation, okay, for that specific site. So let's read the question, what he says. So he says that it's an icy frictionless ground, which means that from the ground, we can ignore the friction for the ground factors. Friction will not exist, okay? And the wall is rough. That means the friction will exist for the wall only. So in option A, I can see that B is only the representation of normal reaction. There is no friction involved because the resultant is not in this direction. I need the wall to be rough. I need the wall to have a friction component. So option A cannot be the answer. Let's move to option B. Looks promising. There is a normal reaction from the wall. There is a friction in the upwards direction, right? So the resultant is in the direction of B. This is fine. Let's move to the second check, which is the frictionless ground. So I realize that the ground is only representing the normal reaction component. The friction component is missing, which is given in the question. So this is our answer for the current situation. But let's explore option C and D, what's happening in those cases. In option C, we can see that there is an only normal reaction. The friction component is missing because if it was present, the resultant would look something like this. So in this situation, if the question was that the wall is smooth, then that would be this case. Okay, the friction is absent. In this case, why P is in this direction? Because there is a normal reaction component from the wall and there is a component of friction. That's why P looks like this. So now it all comes down to you to understand whether friction will be a part of the question or not. Simple as that. Okay.